Hey everyone, can you believe it? We are in the final presentation for astronomical phenomena. We've made it. I know we feel like we've been studying astronomical phenomena forever, but there's just so much stuff happening out there. So the final things that we will look at are eclipses and other things. Well, you'll just have to wait to see. So, what are eclipses? I'm sure you've heard about them a lot, and you've probably tried to look at one with special glasses before. But sometimes the Earth, the Moon, and the Sun are perfectly aligned in space. So, what does aligned mean? Just like what it sounds like, in a line. Okay. So, sometimes they are perfectly aligned in space. When this happens, we observe an eclipse. And there's different types of eclipses. So there are solar eclipses. So think about what solar means. Okay. And lunar eclipses. Think about what lunar could possibly mean. Remember what moon is in French? La lune. All right. So what are the differences? Okay. So a solar eclipse. Okay. So we're over here. Solar eclipses occur when the moon has just moved to a place that is exactly between the earth and the sun, right? So we have earth, moon, sun, or I like to say a moon sandwich. So here we see that. See, they're aligned, right? They're in a line. And the moon is in between the earth and the sun. So that makes it a solar eclipse. Okay, on the other side, we have lunar eclipses occur when the Earth is between the sun and the moon. So we have moon, Earth, sun, and what I like to call it an Earth sandwich, right? So it's what's in the middle. So over here for the solar eclipse, we had the moon in the middle. And for the lunar eclipse, we have the Earth in the middle. Okay, so let's read a little bit more about solar eclipses. All right, so a solar eclipse occur when the moon has just moved to a place that is exactly between the earth and the sun, right? So we said we have a moon sandwich. The moon therefore covers the solar disk. So remember what a disk is. It is as dark as night in daytime. All right, so this is happening in the daytime, but it looks dark as night. Okay, because the moon covers the sun, right? That circular looking disk, the moon covers it. Eclipses can be total, partial, or annular. So a total eclipse. So this occurs when the moon covers a surface that is slightly larger than the solar disk. At this point, a black disk with a luminous contour can be seen, the solar corona. Okay, so what are the things that we are seeing here that are key? So the moon, it's covering the surface of the solar disk or the sun, and it's slightly larger than the sun. So it's practically it's covering it, and then you just see like these little edges coming off there. Okay, so it's a luminous contour, and that's called a solar corona. So that's a total eclipse. We have like this total covering of the solar disk or the sun. A partial eclipse, a partial solar eclipses happen when the moon comes between the sun and the earth, but the moon only partially covers the sun's disk. So here is, so imagine this is the moon and the sun would be totally circular, right? We'd have a disk, a solar disk, but the moon is only partially covering the sun. Then we have an annular eclipse. An annular solar eclipse happens when the moon covers the sun's center, leaving the sun's visible outer edges to form a ring of fire or annulus around the moon. Okay, so over here we see that the moon is covering just the center. It's not covering it entirely like with the total eclipse. So we still see like this ring of fire, right? Because that's the moon here covering the center of the sun. And then this would be the outer part of the sun that is showing. Over here, there was total covering, and you just see like this luminous contour, right? But you're not seeing the same thing as this. So let's just watch a quick video.
A solar eclipse happens when a new moon moves between the Earth and the Sun, blocking some or all of the Sun's rays from reaching the Earth. By cosmic chance, even though the Sun is 400 times wider than the Moon, it's also 400 times farther away. Therefore, the two objects appear the same size in our sky. Astronomers are able to predict eclipses because the Earth and Moon have very predictable orbits. Why then isn't there an eclipse every month? The Moon's orbit is usually tilted a few degrees north or south in relation to the Earth. When the Moon does eclipse the Sun, it casts two types of shadows on Earth: a smaller, darker shadow known as the umbra, and a larger shadow known as the penumbra. There are four types of solar eclipses. The first and most spectacular is a total eclipse, when the Moon completely covers the Sun's surface. A total eclipse can only be seen if you're standing within the umbral shadow. That's why the imaginary line created by this shadow as it races across Earth is known as the path of totality. People within the penumbral shadow see only a partial eclipse, the second type. From this view, outside the path of totality, the Moon passes in front of the Sun off-center, never fully covering its surface. Third, an annular eclipse occurs when the Moon passes directly in front of the Sun. However, unlike a total eclipse, the Moon appears too small to fully cover the Sun. The Moon's orbit is elliptical, so sometimes it's closer to Earth and sometimes it's farther away. Last, a hybrid eclipse is when the Moon's position between the Earth and Sun is so finely balanced that the curvature of the Earth plays a role. The Moon will be farther away from some parts of Earth along the eclipse's path, resulting in an annular eclipse. In other parts, the Moon will be just close enough to fully cover the Sun, resulting in a total eclipse. While a total solar eclipse happens somewhere on Earth every year or two, any given point on Earth experiences the event only about once every 400 years. We interrupt this video for an important safety announcement. Looking directly at the Sun, even during an eclipse, can cause permanent eye damage. Fortunately, there are ways to enjoy an eclipse safely. The easiest is to use certified eclipse watching glasses, which are shaded thousands of times darker than typical sunglasses. You can also look at the eclipse indirectly by making a pinhole viewer. Simply poke a small hole in a piece of cardboard. Hold the cardboard up to the Sun, allowing the Sun's image to be projected onto a flat surface. Be sure to look only at the surface and not through the cardboard. Just before the Moon completely covers the Sun, low-lying valleys on the Moon's edge will be the only spots that sunlight continues to pass through. These remaining brilliant shafts of light, known as Bailey's beads, will disappear one after another. And finally, a single bead of light remains, known as the diamond ring, signaling that you're just seconds away from experiencing totality. Once the last bead disappears and the Moon completely covers the Sun's surface, the view through your eclipse glasses will be pitch black. Totality achieved. At this point, none of the Sun's rays are reaching your eyes, and it's the only time that it's safe to take off your glasses. Remember to put your eclipse glasses back on before any of the Sun's rays start to peek through again. Any sunlight reaching your eyes, even for a few seconds, can cause serious damage. While an eclipse can last a few hours, totality typically occurs for less than 3 minutes. Animals and plants have also been known to alter their behavior during a total eclipse. Songbirds may stop singing, crickets may start chirping, and flowers may even start to close up. We won't always be able to see total solar eclipses. The moon moves about 1.5 inches away from Earth each year. It's estimated that in about 1 billion years, the moon will be too far away from Earth to completely cover the sun. A solar eclipse.
All right, so we just looked at a solar eclipse, and let's talk a little bit more about the lunar eclipse. So during a lunar eclipse, Earth gets in the way of the sun's light hitting the moon. That means that during the night, a full moon fades away as Earth's shadow covers it up. The moon can also look reddish because Earth's atmosphere absorbs the other colors while it bends some sunlight toward the moon. Sunlight bending through the atmosphere and absorbing the colors is also why sunsets are orange and red. During a total lunar eclipse, the moon is shining from all the sunrises and sunsets occurring on Earth. So remember that the lunar eclipse is what kind of sandwich? Is it an, let's go back. What kind of sandwich did I say it was? Okay, an Earth sandwich, solar eclipse, a moon sandwich. All right, so we're just going to look at the video that talks about a lunar eclipse.
A lunar eclipse happens when the Earth blocks some or all of the sun's direct light from reaching the moon. This cosmic event only takes place during a full moon, which happens once every 29.5 days, or the length of one full orbit of the moon around the Earth. So why don't we have an eclipse every month? The moon's orbit is tilted a few degrees in relation to the Earth, so the Earth, moon, and sun don't always align. When the Earth does eclipse the sun, it casts two types of shadows on the moon. A larger shadow, known as the penumbra, and a smaller, darker shadow, known as the umbra. There are three types of lunar eclipses. The first is a total lunar eclipse, when the sun, moon, and Earth are in perfect alignment and the moon falls within the Earth's umbral shadow. Total lunar eclipses are the most striking of the three types because they turn the moon a sunset red. While shorter blue wavelengths of light are scattered outward by the Earth's atmosphere, longer red wavelengths are refracted or bent inward toward the moon, making it appear red. The brightness of the moon's red glow depends upon how much dust and clouds are in the Earth's atmosphere. Following volcanic activity, ash can block out enough light to render the moon a darker red or even near black. A partial lunar eclipse, the second type, occurs when the Earth, moon, and sun don't perfectly align, so only part of the moon passes into Earth's umbra. Earth's shadow appears very dark on the side of the moon facing Earth. Last, a penumbral lunar eclipse occurs when the moon passes through Earth's penumbral shadow. The event is so subtle that most people don't even notice. The moon will appear just slightly darker than normal. Lunar eclipses occur up to 3 times a year and can be observed from the entire nighttime half of the Earth. Unlike during a solar eclipse, it's safe to look at the moon with the naked eye during a lunar eclipse. It is only because of the distances of the sun and moon from the Earth that we are able to witness total lunar eclipses. As the moon inches away from the Earth each year, one day, billions of years from now, the moon will be too far away to fall completely within Earth's umbral shadow. Until then, we can occasionally enjoy seeing our own planet's shadow cast upon the largest object in the night sky.
All right, So you are required to go read pages 374 to 375 so that you can see what your textbook has to say about eclipses. So the text in the slide comes mainly from your textbook, but I would like you to read your textbook yourself. So, we were just basically talking about after we were looking at the planets in the solar system, we asked, well, what else is out there? So, we started looking at other celestial bodies. You guys read about comets, you read about meteoroids, asteroids, and all those things. And then we're moving on to see, well, what else is out there? What else is happening? So you must have heard about polar auroras, or you've heard about them in terms of northern lights or southern lights. So polar aurora is a phenomenon caused by the solar wind. So you guys learned about solar wind and had to include it in your crossword puzzle challenge. When the solar wind particles arrive near the Earth, they are diverted towards the poles. So you're talking about the North Pole and the South Pole. This is why the auroras are observed primarily in the polar region. So that's what we were just talking about, North Pole versus South Pole. There are two types of polar auroras. The aurora borealis appears in the northern hemisphere, and the aurora australis occurs in the southern hemisphere. Okay, so here is your northern hemisphere. This is up here. Remember, you see them mainly in the poles. So this is North Pole. So we'd be talking about aurora borealis or northern lights in the northern hemisphere. And in the southern hemisphere, we are calling them aurora australis or the southern lights. So I would like you to go through this page, which is given to you by NASA. So let's check it out. So this page gives you all this information. What is an aurora? If you're ever near the North or South Pole, you may be in for a special treat. Frequently, there are beautiful light shows in the sky. These lights are called auroras. If you're near the North Pole, it is called an aurora borealis or northern lights. If you're near the South Pole, it is called an aurora australis or southern lights. So what makes this happen? Even though auroras are best seen at night, they are actually caused by the sun. The sun sends us more than heat and light. It sends lots of other energy and small particles our way. The protective magnetic field around Earth shields us from most of the energy and particles, and we don't even notice them. But the sun doesn't send the same amount of energy all the time. There is a constant streaming solar wind, and there are also solar storms. During one kind of solar storm, called a coronal mass ejection, the sun burps out a huge bubble of electrified gas that can travel through space at high speeds. When a solar storm comes towards us, some of the energy and small particles can travel down the magnetic field lines at the north and south poles into Earth's atmosphere. Remember that word atmosphere. Think about what it is. So over here we see the sun, you see the solar wind, and this magnetic field. There, the particles interact with gases in our atmosphere, resulting in beautiful displays of light in the sky. Oxygen gives off green and red light. Nitrogen glows blue and purple. So these are gases, right? Oxygen's a gas, nitrogen's a gas. Do other planets get auroras? They sure do. Auroras are not just something that happen on Earth. If a planet has an atmosphere, so you remember the atmosphere has gases, and magnetic field, they probably have auroras. We've just seen amazing auroras on Jupiter and Saturn. Now, something really interesting I had asked you to read the other day in regards to Jupiter and Saturn. Do you guys remember what that was? You were supposed to read an article. So, here we're about to witness a super rare planetary alignment not seen in 800 years. Stargazers are in for a treat over Christmas as Jupiter and Saturn will get closer to each other in Earth's night sky than they have been for nearly 800 years. Set up your telescope, hope for a clear night, and get ready. So I won't read the whole thing because you were supposed to do it, but let's just read over here. The celestial synchronization has been in the works since summer as Jupiter and Saturn have been moving closer together in the night sky. And between the 16th and 25th of December, they'll be separated by only 1/5 the diameter of a full moon. While the planets won't physically be close to each other at all, of course, they'll look like a single point of bright light to anyone looking up at the night sky. Alignments between these two planets are rather rare, occurring once every 20 years or so. But this conjunction is exceptionally rare because of how close the planets will appear to one another, says astronomer Patrick Hartigan from Rice University. You'd have to go all the way back to just before dawn on March 4th, 1226 to see a closer alignment between these objects visible in the night sky. To get the best viewing experience for this spectacular show, you're going to need to be somewhere near the equator. But if the skies are clear, then the alignment should be visible from just about anywhere on Earth. We are not close to the equator, unfortunately, guys. So I encourage you to read this again if you haven't, right? You were supposed to read this. This was a part of your assignment of reading assignments. So please read it. Let's go back to our presentation. Let's look at this video.
Here's a story. Now, imagine there's an invisible force field around our planet. And now imagine that for billions of years, that force field's been protecting us from a beam of supercharged plasma that would otherwise wipe out life on Earth as we know it. Now, you might think this is some kind of science fiction story, but it's all true. And it's what gives us this, the aurora. So the aurora is one of mankind's oldest mysteries. We've come up with some crazy theories of how to explain it along the way. Take Aristotle. He thought the aurora was the sky vomiting little bits of flames. But it wasn't until the 1600s that we figured out two key things that helped us explain the aurora. One, the Earth is really just one big magnet. And second, it turns out that the sun gives off a lot more than just light. Long before any sunlight hits Earth, it's born at the edge of the sun. At the edge of the sun, the corona is a busy, beautiful place, full of churning whirlpools of plasma and huge magnetic arcs. All that action is constantly releasing waves of energized particles, creating what we call the solar wind. Now, a few days after leaving the sun, traveling at a whopping 400 kilometers per second, that blast of charged particles reaches Earth. But luckily, we've got a secret weapon on our side, Earth's swirling molten core. Our core is the key to life on Earth. It creates a magnetic force field around us that deflects the solar wind up and away, making life down here much more enjoyable. Now, because of that magnetic field, we have nice things like an atmosphere, and we're much less burned to a crisp thanks to wave after wave of planet sterilizing radiation. But despite all that, a tiny bit of that solar wind does hop on the magnetic field and ride it up or down to the Earth's poles. And that's where we get the auroras. When those energized particles smash into gases way up high in our atmosphere, they excite them, which means the gas atoms grab onto a bit of energy. But they don't stay excited for long. They give off that stored energy in a bright burst of light. Different atoms in our atmosphere each give off different colors. Excited oxygen is what gives off that familiar green and red that most of us think of when we hear aurora. But there's also nitrogen up there, and it can give off a really cool mix of red and blue light that makes the sky glow this incredible purplish pink. Now, we can only see this happening at night, but it's happening 24 hours a day, every day of every year. It's also happening on Saturn and Jupiter. Sometimes the sun takes that wind and turns it up to 11, and that can be a very dangerous sight to behold. Now, extreme solar storms called coronal mass ejections can erupt into space almost without warning, unleashing huge waves of charged particles. And if they happen to be pointed at Earth, then look out. Now, these storms are incredibly powerful. Astronauts that are working outside of the Earth's magnetic field say that if you close your eyes during one of these solar storms, you'll see bright flashes of light from the charged particles reacting with the fluid inside your eye. And in 1859, a storm so powerful hit Earth that it powered a telegram from Boston to Portland, Maine, with the equipment unplugged. When those rare violent storms hit Earth's magnetic field and ride up to the polar atmosphere, we're treated to an aurora show like no other. Now, these images are more than just works of art. They let scientists study how solar storms affect life here on Earth, like our electronics, our communications. Some of the best views of Earth's auroras have been captured from the International Space Station. The space station passes near the north and south poles of our planet about once every 90 minutes. So if they pass by the poles when it's dark, the auroras are close enough to reach out and touch, although I wouldn't recommend that. NASA makes sure that the astronauts that work on the ISS are highly trained photographers, and artists down here on Earth are taking their photos and remixing them into creations that are enough to blow your mind. This celestial light show has been burning bright for perhaps billions of years, and it's more than just Earth's private art show. It's painted by an invisible force that surrounds our living planet, a force that catches wind from the sun and turns it into light. It gives humans a constant reminder of the beauty of the night sky, and it's right there in our planetary backyard. And that's pretty awesome. Thanks a lot for watching, everybody. Click to subscribe. Check the description to follow us on Twitter and find a link to the blog. Here's a story. Now, imagine there's an invisible force field around our planet.
So we'll just watch another quick video. Oh, that is so beautiful. So now you are required to go back to page 367 and read about the polar auroras. And that concludes our section on astronomical phenomena. We did it, guys. So, again, you will need to do the textbook readings because you will have a quiz coming up very, very soon. And if you do have any questions, please don't hesitate to email me at hinksons@loyola.ca. Take care.